Hey guys, last lecture in thermodynamics, this ought to knock it out. So we've mentioned this word enthalpy a few times, and you probably remember it from your previous chemistry classes, but we're talking about how much heat is in the system at any given time. We give it the variable H, so delta H is the heat of the products minus the heat of the reactants, or the final heat in the system minus the initial heat in the system. We don't really have a way to identify exactly what the enthalpy of a substance is at any given time, because it has to take into consideration so many different factors. The kinetic energy, I mean, if you think about the way these molecules are moving, right, they can be swiveling around bonds, they can be vibrating in different directions, along bonds, across bonds, they can move through space with rotation, they can on any axis. So, it's a very hard thing to kind of pin down the amount of enthalpy that's actually in a substance. So we can't get any of these things, but what we can get is how much they change. So we'll have a reaction like this. So I've got iron rusting here. I'm making iron oxide. And I know that this produces heat, 1,625 kilojoules of heat to produce 2 moles of iron oxide. So what that means is the heat of the products plus some amount of energy equals the heat of the reactants. So that means that the enthalpy in the products has got to be less than the enthalpy in the reactants because heat came out. But if you're looking at all the values I've got here, we don't know the enthalpy of the products. We don't know the enthalpy of the reactants. So we don't know any of this stuff except for how much it changed, how much was released. That's something we can measure. What comes out or what goes in, we can measure those. We can use temperature to find a value. So that value, that is delta H. That's the change in enthalpy. So usually we'll just write the chemical reaction and then say that this reaction has a delta H of and give a value. And so you should be cool with that negative sign there, right? This is a negative delta H. That means it's coming out of the system. It's being taken away from the system. It's being subtracted from the system. So that's released into the surroundings. If it were a positive delta H, we would have to put that much energy in to make the reaction happen. So remember, with the negative signs, it's always going from system to surroundings. For positive, it would be surroundings to system. So we always have a graph that looks like this. Whether our products or reactants have more or less energy, it doesn't matter. It's always got this bump in it, right? We always have to go up and then go back down, which means we always have to put energy in, regardless of how much we get out. Either we'll get a little bit out or a lot out. Maybe we'll get more out than what we put in. Maybe we won't. But we always have to put some in. And that energy going in, that's the energy it takes to break bonds. Both of these are exothermic reactions, meaning heat energy is going to be coming out of there because we have a negative delta H in both cases. But energy is absorbed by the reaction, like I said, first, and then energy is released. So energy goes in and then energy comes out. And it doesn't matter. If it were an endothermic reaction, it would look more like this, right? But still, we would have to put energy in and get energy out. We would just get out less than what we put in. The source of the energy is, from the environment, from the surroundings. So bond enthalpy is the energy in bonds. It's how much energy it takes to break a bond, or it's also the energy you get out when you form a bond. And so it's going to be the same value, just a different direction. I'm going to put energy in to break a bond, and I'm going to get energy back out when I form that bond. Or if I form a bond and then break it, but it's going to be the same value. We can find the enthalpy of a reaction by adding up the enthalpies of all the bonds that are broken and subtracting from that all the bonds that are formed. The bond energy that we have to overcome to break the bonds in the reactants, and the bond energy that we get when we form the bonds in the products. Now, this is always going to be an approximation, because if I've got 2 carbons stuck to each other, it matters what else is on there. So if I have a double bonded oxygen, say this is a carboxylic acid over here, that's going to make this bond have a slightly different strength than, say, if I had just 3 hydrogens on here. That's going to affect the strength of that bond. So what we have is actually an average. If we say the bond enthalpy between a carbon and a carbon, that's just an average for all carbon-carbon bonds. But they can be different based on what else is stuck to the carbon. So we have a little table here, and you've got this on your handout. And so this is a bond enthalpy practice problem. So you're going to need to pause the video and solve this problem, and then play it again if you get stuck, or play it again when you're done so you can check your answer. So to find the enthalpy of a reaction, going back to this, I'm going to do this right here. So I'm going to take the bonds that are broken, subtract from that the bonds that are formed, the energy for each of those, the enthalpy for both of those. So the bonds that are broken, I've got, this is going to be one of these guys, right? An HH bond. So that's 436. So delta H equals 436 plus, I need a half of an O2. Now O2, remember, is double bonded oxygen. Like that guy right there. And sometimes it helps to draw these so you don't forget that there are double bonds and things like that. So double bonded oxygen is 498. So I need a half of that. Now you might think, how can you have a half of an O2? It's not a half of an O2. It's half of a mole of O2, right? Because this is kilojoules per mole. So half a mole, oh, well, that's the thing we can do. Take that whole thing and we're going to subtract from that. Water is this guy. Again, I don't think it's a bad idea to draw it. You got two OHs, so 2 times whatever the OH bond is. OH is here, 464, so 2 of those. So 2 times 464. So we're going to add all that together, and we get negative 243 kilojoules per mole. Again, if I make any mathematical mistakes, send me an email. I'll send you back virtual Smarties as a reward. So here's another practice problem, a lot like the first one. Remember, you have to, of course, balance the equation first. So go ahead and pause the video and do this one. So a single mole of methane, I'm doing CH4 plus, and you got O2 because it's a combustion reaction, right? And you're always going to have that oxygen. And that's going to yield CO2 and H2O. And again, that's just what all combustion reactions are like. And you should know that. Looks like the carbon's already balanced. I'm going to balance the hydrogen by putting a 2 here. That means I'm going to need a 2 here because I've got 2 oxygens here and 2 there, so a total of 4 oxygens. So this is good to go. So when we go to do this math, I'm going to need 4 of these, 2 of these. Carbon dioxide is double bonded oxygen, so carbon double bonded to oxygen. That's this guy right here. And then I'm also going to have 2 waters, which means a total of 4 OHs, right? So where'd my OH go? So I need 4 of these. So it's going to be this and this added together minus the other 2. Oops, going to need 2 of these. So there we go. This is the equation you'll end up with. The delta H of the reaction is going to be equal to these guys right here. And that should get you negative 676 kilojoules per mole. I didn't leave myself much room in here. It's kind of messy, but negative 676 kilojoules per mole should be your answer. So we know delta H from experimental evidence for a lot of different reactions. It's not an easy process to get delta H for every single reaction. So what we can do is just take the ones we know already and use those to estimate our delta H for any other given reaction. So we can take our published delta H values, and sometimes with a few tweaks and adjustments, we can make a new reaction enthalpy. Let's say we didn't know delta H from here to here. We didn't know this negative 283 kilojoules. If we didn't know that, but we knew this one and we knew this one, we could do a little subtraction and figure out what this one is, because we start out with these reactants and end up with these products. Either one of these pathways, it's got to be the same amount of energy, because it's the energy that's in these bonds and these other bonds. And so we can find these things this way. So basically, Hess's law is saying that the sum of the steps are going to be equal to the overall reaction. So that makes a lot of things possible. So when you're given like steps in a reaction, sometimes you'll be given the enthalpies of steps, and you have to figure out what the overall enthalpy is. You remember when we did kinetics, we had elementary reactions and we had overall reactions. This is kind of that same idea. We can take those steps and add them up to figure out what the overall reaction's enthalpy change would be. Sometimes the steps we have are not exactly the steps in order. Sometimes we have to reverse them. Sometimes we have to multiply them by some factor. We can do that. That's totally acceptable. If you end up having to flip a reaction, let's say there's something in the reactants that you need in the products, you just flip the sign too. So if it's a negative delta H, you flip the reaction, now it's a positive. Same value, but positive. And if you need 2 of a particular product or something like that, you can double the reaction. And so all you have to do is double the delta H. And if it's 30 times or 0.2 times, you can work that out every time. We have something called the heat of formation that we'll talk about here in a minute, but just as a intro here, you take elements and make a particular product. That's the heat of formation, the amount of energy it takes to take elemental forms of each atom, right, and make that compound. That's the heat of formation of that compound. So find the standard heat of formation of SO3. So what's it take to make SO3 from its elements, which means from a sulfur and 1.5 O2s, because oxygen in its elemental form forms a diatomic, right? So this is what you need to get the heat of formation. This yields SO3. So I want the heat of that reaction, the change in enthalpy of that reaction. That will give me, that is the heat of formation of SO3. So let's see how we can get there. I've got the S already going in, and I've got 2 of the O's, but I need another 1/2 O2, right? I'm missing a half O2. And we also are not making SO3, but I'm going to leave this reaction. So I'm going to need this value because I'm going to need this reaction just like this. But the second reaction is not very helpful the way it is. I need a half an O2 on the left-hand side, and I need to get this SO3 on the right-hand side, but I need to get rid of that too. So I'm going to flip this reaction. So I'm going to make this negative 198. And then I'm also going to divide it by 2 because I wanted this to just be a single SO3, and I want this to be a half of an O2. And again, you may be going, what's a half of an O2? That's just an O. That's not the same thing, first of all. And second of all, it's moles, right? It's moles. So half a mole of O2. So since I'm going to divide it by 2, I have to divide the delta H by 2, so that gets me 99 kilojoules. Negative 99 kilojoules is what I'm going to use. So I just have to add these two values together, and that gives me the standard heat of formation. So this is going to end up looking like 1/2 O2 plus SO2 yields SO3. So the SO2 is going to cancel. And I've got this, I've got that. So that's my 3/2 O2. I've got my sulfur, and I've got my SO3, and everything else is gone. And when I add those together, I get negative 396 kilojoules. That's my delta H of formation. So this is a practice problem you've got on your packet. Go ahead and try it and pause the video. So we're looking at this one. I'm trying to make this reaction happen. So it looks like I've got the NO here, no problem, but that's not useful. That's not useful. That's nothing else there is useful. But this reaction has NO on the reactant side, and that's where I want it to be. So I'm going to keep this one the way it is. This value down here, I want to get rid of this O2. Looks like I can do this. If I use this one, if I flip this, then I get 3/2 O2 yields O3. And now my O3 is gone. I got rid of that. And if I cancel that out, I'm going to end up with not 3/2, but 1/2 O2 on this side. So let's see if I can get rid of that. And it looks like I can in this last reaction. So I'm flipping this one, and that's all. And then this last one, I'm going to flip it, and I'm going to divide by 2 because I want to get oxygen yields 1/2 O2, and that cancels my O2s and gives me my oxygen for this reaction up here for the overall. So my overall reaction now, I've got this guy going in, I've got this guy going in, and then my products are just NO2. Everything else is canceled out. So what did I have to do? I had to flip this. So I'm going to need negative 198.9 because I left that one alone. I'm going to need positive 142.3 because I flipped that reaction. And then this other one, I flipped it and divided it by 2. So that's going to give me negative 247.5. And if you add all those up, you get negative 304.1 kilojoules per mole. So like I said before, the enthalpy of formation, which a lot of times we put a little degree symbol here too, that's defined as the change in enthalpy to form a substance out of atoms in their elemental state. So you got to keep in mind the 7-Up, the diatomics, or what was Keister's rule? Honkel fiber? I think that was it. It was either that or no. These are known for a lot of substances. Here's a table of a bunch of them. And if you look, most of them are negative values, and that shouldn't be surprising because you get more energy out when you form bonds than when you break bonds, right? So you don't really have to break very many bonds to do these things, except for when you have diatomics. And so sometimes you can get a positive value. These are all values at STP. So to make water vapor, for example, you're going to take 1 mole of hydrogen gas and 1/2 mole of oxygen gas to make H2O. Now, elements, their standard enthalpy of formation is always 0 because it takes nothing to make O2 gas out of O2. It is O2. So that makes some of our math a little easier. So you can use these standard enthalpies to get to products of a reaction that you don't necessarily know the delta H of. So you could use the standard enthalpy of C3H8. So you're going to make some graphite, the carbons, and you're going to make some H2 gas. Plus you've got this O2 gas for this combustion reaction. All right, so that's there. All we did though was we used the standard enthalpy to get to here. And then we can use the standard enthalpy to make CO2. That gets us down to here. We've still got the hydrogen and the oxygen to deal with, so we need the standard enthalpy of the formation of water to get us to here. And so now we can find the change of enthalpy from the reactants to the products of this reaction by using standard enthalpies. Again, this is just Hess's law. The steps you have to take to get there, added and subtracted, can get you to the overall reaction. So we can apply Hess's law to standard enthalpies. And basically it looks like this. The delta H of any given reaction is equal to the sum of all of the standard enthalpies of the products minus the sum of all of the standard enthalpies of the reactants. This N and M, those are the coefficients for each one. So, if it's, 4 waters in a reaction as a product or something, you would have a 4 before you did the standard enthalpy of water. Probably easiest to see that when we do it. So let's try this one. So you're going to try and find the standard enthalpy of copper oxide using the rest of these standard enthalpies and knowing that delta H of this overall reaction is this. So I'm going to leave it just like this and tell you to pause the video. Get started on it. If you get stuck, unpause, watch me do a step, and then pause it again. And then see if you can get it the rest of the way. And just continue to do that until you've got it. So pause the video now. So going back to this, here's Hess's law with standard enthalpies. So it was delta H, so it's going to be this guy. That one right there equals the standard enthalpy of the products minus the standard enthalpy of the reactants. So here's the products. I got copper solid and water. Copper solid, that's elemental form, so that's 0. So the products is going to be 0 plus the H2O. They gave us that is negative 285.8 minus the reactants. So the reactants are the standard enthalpy of the formation of copper oxide, so delta H of formation CuO, plus hydrogen, which of course is going to be 0 because it's elemental. And if we go back to this delta H at the beginning here, this is going to be negative 129.7. So now all I have to do is solve for this guy. So you rearrange the equations, solve for the heat of formation of copper oxide, and you'll get negative 156.1 kilojoules per mole. This next problem has a number of things wrong in it on your paper version. I've changed them on here, so use this version. You were actually missing some numbers. So the first one you should be able to do on your paper just fine, but this second part here, you definitely need more numbers. You need this number right here, which I didn't give you. Also, I changed the number of the water because it should be water vapor, not water in the liquid form. And I think on your paper, I made it the liquid form. So go ahead and pause the video and answer all of this if you can. And if you get stuck, unpause it and then pause it again once you're unstuck. All right, here we go. This equation is C3H5N3O9 yields, looks like CO2, right, carbon dioxide, plus water, plus oxygen gas. So we're going to balance this equation. I'm going to put a 3 here because I'm balancing the carbon. I'm going to balance the hydrogen with, okay, so I got a problem. I got an odd number coming in and an even coming out. So I got to put a 2 here, and I'm going to turn that into a 6, and I'm going to put a, so this would be a 5 here. Now let's balance the nitrogen. Looks like there's 6, so I'll put a 3 right there. Now my oxygens, I've got 18 oxygens going in. So I've got, let's see, this is 12. This is 5. So that's 17 total. And I need one more, and I've got O2. So I can't have one more. I got to have two more. When you're balancing equations, you can't use fractions. So I've got to double it again. I'm going to put a 4 here, make this a 12, make this a 10, make this a 6, and then this can be a 1 instead of a half. And now it's all balanced. If you don't believe me, add them up. We go to calculate the standard heat of formation of this trinitroglycerin. Given that this is the delta H for this reaction up here, I've got the standard heat of formation of water. I've got the standard heat of formation of carbon dioxide as well. So think about your equation. You're going to have the delta H of the entire reaction is equal to the standard enthalpy of the reactants minus the standard enthalpy of the products. And you got to take into consideration all those coefficients. So in this case, the heat of the reaction is negative 5660. That's going to be equal to, now let's do the standard enthalpies of, I'm going to do this in brackets, standard enthalpies of the products, which is going to be 12 times the CO2 value, which is negative 393.5, plus 10 times the water value, so 241.8, and that's water in gaseous form. It's a little different for liquid, plus N2 and O2, but those are both elemental forms already, so those are both 0. So I'm just going to bracket that out right there. That whole thing minus the standard heat of formation of, I'm just going to put Ng for the nitroglycerin. Oh, and don't forget, it's going to be 4 of those in this reaction, right? So got to have that 4 there. So, but this is what I'm trying to find, right? The standard heat of fusion of the nitroglycerin. So let's rearrange this equation to solve for that. So I've done some rearranging and a little bit of simplification, but there's my CO2, there's my water. Remember, the nitrogen and the oxygen are zeros, so nothing there. This is my heat of reaction, and that's got it all set up to solve for the standard heat of formation of that nitroglycerin. I'm dividing by 4 down here because remember, that was 4 of the trinitroglycerin is what gave us that 5660. It's also what gave us 12 of these and 10 of these, right? The CO2 and the water. So that'll get us the standard heat of formation of a single mole of the trinitroglycerin. And that should be negative 370 kilojoules per mole. So this one's pretty straightforward. It just wants to know how much energy comes from 0.6 milligrams of this stuff. This is basically a conversion problem. So I'm going to make that 0.00060 grams of the trinitroglycerin. I'm going to multiply that. I need to convert it into moles. So how many grams are there in 1 mole of this? You have to add up a whole bunch of carbon, hydrogen, nitrogen, and oxygen, but eventually you'll get 277.1 grams. And that'll get you a very small number, 2.165 times 10 to the negative 6, right? And that's in moles. So now we've got it in moles. It's a very, very small number, but we want to get rid of the moles. We know it's negative 370 kilojoules per mole. So our moles will go away now if we just multiply that, and that'll get you, it's 0.000801 kilojoules, but I'm just going to call it 0.801 joules. That makes it a little nicer number to write. So if this melts at 3 degrees Celsius, that's a pretty low temperature. I mean, you're going to be encountering it as liquid most of the time. From that information and from the formula, which the formula is right here, carbon, hydrogen, nitrogen, and oxygen, all non-metals. What does that tell you whether it's molecular or ionic? So the fact that it is all non-metals and it has a relatively low melting point tells us that it's a molecular compound, right? Ionic compounds tend to have high melting points. Ionic compounds are going to have metals in them typically. All right, so describe the various conversions of energy when trinitroglycerin is used as an explosive to break rock faces in highway construction. So it's going to start out as chemical energy, right? That's energy stored in those bonds. When we break these bonds, it takes a little bit of energy to break them, but we get a lot of energy out. Think about what's going on. We're turning that liquid into gases. We're turning it into a lot of gases with kinetic energy, small particles with a lot of kinetic energy. If we do this in a confined space, it's just the way you do this. You don't blow this stuff up on the surface because that wouldn't make a hole. You drill a hole, put the stuff in there, and then the only place that the gas has to expand is outward, and that has to push those rocks apart. It busts those rocks up. So kinetic energy is coming out of there. We're getting heat, we're getting kinetic energy, and eventually all that kinetic energy will be dissipated as heat as well. So chemical energy is where you start. You get some heat and kinetic energy, and then the rest of the kinetic energy will also be dissipated as heat. Pretty straightforward as far as that goes, and not something you need to worry too much about. So that's the last lecture for Unit 6. Hang in there, guys. You're doing great.